Before we dive into humanity's cosmic shield, drop a comment about what space threat worries you most. If you enjoy these explorations of our universe's dangers, consider subscribing. These investigations into our survival strategies are meant to be shared. Right now, massive rocks are hurtling toward Earth at speeds that would vaporize anything in their path. You can't see them coming. Most will miss us by millions of miles. But some won't miss. You might think asteroid impacts only happen in movies. The dinosaurs thought the same thing 66 million years ago, until a mountain-sized chunk of space rock ended their 165 million-year reign in a single day. Tonight we're discovering how close these cosmic bullets come to hitting us, and how humanity plans to deflect them before they turn our cities into craters. Dinosaurs ruled Earth for over 160 million years. Then 66 million years ago, their reign ended in a single day. A space rock, what scientists call an asteroid, slammed into Earth near what is now Mexico. This wasn't a pebble. The asteroid measured roughly 10 kilometers across, about the size of a small mountain. When it hit, the impact released more energy than every nuclear weapon on Earth exploding at once. Scientists know this happened because they found the smoking gun buried in rock layers around the world. A thin line of unusual metal called iridium, common in space rocks but rare on Earth, marks the exact moment the dinosaurs died. Below this line, you find dinosaur bones everywhere. Above it, nothing. They simply vanished. The collision was so violent it melted rock and blasted it into space, where it cooled into tiny glass beads before raining back down. The impact triggered massive waves that swept across continents and threw so much dust into the air that sunlight disappeared for months. 75% of all life on Earth died in the aftermath. One asteroid had ended the age of dinosaurs and cleared the stage for mammals, including our eventual ancestors, to take over. February 15, 2013 started as an ordinary winter morning in Chelyabinsk, Russia. Then a fireball brighter than the sun streaked across the sky. A space rock about 20 meters across, roughly the size of a house, plunged into Earth's atmosphere at incredible speed. The rock didn't even reach the ground. It exploded in midair, 30 kilometers above the city, releasing energy equivalent to dozens of atomic bombs. The explosion created a massive shock wave that raced toward the ground. Windows shattered across an area 200 kilometers wide. Over 1,500 people were injured, mostly by flying glass. The sound was so loud it traveled around the entire planet twice. Car dashboard cameras recorded the whole thing, showing a brilliant streak of light followed by a blinding flash. People knocked off their feet, buildings damaged, an entire region terrorized by a rock the size of a small building. Here's the terrifying part. Nobody saw it coming. This asteroid was too small for our telescopes to spot ahead of time. Yet it had enough power to level a city if it had hit the ground instead of exploding in the air. Size doesn't matter when it comes to asteroid destruction. Even a relatively small space rock can unleash apocalyptic power. Consider an asteroid just 100 meters across, about the length of a football field, traveling at typical speeds of 20 kilometers per second. This modest rock would hit with the force of several hundred nuclear weapons. The math is simple but terrifying. Energy equals mass times velocity squared. High speeds turn even small objects into civilization killers. A 500-meter asteroid would explode with the power of the largest nuclear bomb ever tested, but spread that destruction across thousands of square kilometers. A 1-kilometer rock could end modern civilization as we know it. And remember, these aren't rare mountain-sized monsters. Thousands of these potential city killers orbit near Earth right now. The physics work against us in every way possible. Space rocks don't slow down like bullets traveling through air. They maintain their cosmic speeds all the way to impact. More speed means exponentially more destruction. Even a car-sized asteroid becomes a weapon of mass destruction when it's moving at interplanetary velocities. When an asteroid hits Earth's atmosphere, the real terror begins before it even touches the ground. The atmosphere itself becomes a weapon. High-speed impacts compress the air in front of the asteroid into a superheated plasma, gas so hot it glows like the surface of the sun. This blazing shock wave races ahead of the rock, incinerating everything in its path. The heat is so intense it can cause third-degree burns from hundreds of kilometers away. The compressed air creates a blast wave that travels faster than sound, arriving before you'd even hear the asteroid coming. This invisible wall of pressure can flatten forests, shatter concrete buildings, and kill people through pure atmospheric violence. It's like standing next to an enormous explosion, except the explosion moves at supersonic speed. Even if the asteroid explodes in mid-air like the Chelyabinsk rock, the atmospheric effects remain devastating. The fireball radiation can ignite fires across vast areas. The shock waves can damage buildings far beyond where any debris lands. The atmosphere we breathe and depend on for protection becomes our enemy during an asteroid impact. The very air around us turns into a weapon that can kill from distances far greater than the impact site itself. An asteroid hitting the ocean creates something far worse than a typical earthquake tsunami. It spawns a wall of water that can cross entire continents. When a space rock slams into seawater, it doesn't just create waves. It carves out a temporary crater several kilometers wide. Water rushes back to fill this void, but the violence of the collision sends massive waves racing outward in all directions. These aren't normal tsunamis. They're moving mountains of water traveling at jet aircraft speeds. A modest 1-kilometer asteroid hitting the Atlantic Ocean would send waves over 100 meters high racing toward every coastline. Within hours, these liquid mountains would devastate every major city on 3 continents. New York, London, and coastal Africa would face walls of water taller than skyscrapers traveling faster than any evacuation could move. The waves don't stop at the beach. They penetrate inland for hundreds of kilometers, turning valleys into temporary seas and destroying everything in their path. Even landlocked areas far from the impact site face destruction as the waves follow river systems deep into continents. Ocean impacts represent the ultimate force multiplier for asteroid destruction. A single rock can simultaneously attack every coastal nation on Earth with tsunamis that make natural disasters look like gentle rain. The deadliest part of a major asteroid impact isn't the explosion. It's the months of darkness that follow. When a large asteroid hits, it blasts millions of tons of dust and debris high into the atmosphere. This material doesn't settle quickly. Instead, it forms a global cloud that blocks sunlight from reaching Earth's surface. Scientists call this an impact winter, and it's exactly as terrifying as it sounds. The dust cloud acts like a massive curtain drawn across the entire planet. Temperatures plummet globally as crops fail and ecosystems collapse. The photosynthesis, the process plants use to convert sunlight into energy, essentially stops worldwide. The entire food chain, from algae to apex predators, faces starvation. This is how the dinosaur-killing asteroid worked. The initial impact was devastating, but the global winter finished the job. Most dinosaurs didn't die from the explosion or tsunamis. They starved to death in a world where the sun had effectively disappeared for months. modern civilization would be even more vulnerable. Our global food systems, dependent on industrial agriculture and international trade, would collapse within weeks. An impact winter doesn't just threaten the region where the asteroid hits. It threatens every living thing on Earth. Earth sits in a cosmic shooting gallery, and the bullets arrive on a predictable schedule. The question isn't whether we'll get hit, it's when. Small asteroids like the Chelyabinsk rock hit roughly every decade. City destroyer impacts, rocks capable of leveling metropolitan areas, strike about every few centuries. Civilization-threatening asteroids, those large enough to disrupt global society, arrive approximately every few 100,000 years. The largest impacts, those capable of causing mass extinctions like the dinosaur killer, happen roughly every 50 to 100 million years. These numbers might seem reassuring, but they represent averages across geological time. The next civilization killer could arrive tomorrow, or it could wait another million years. We've already been hit by several smaller city destroyers throughout human history, though most struck uninhabited areas or exploded harmlessly over oceans. The 1908 Tunguska event in Siberia flattened 2,000 square kilometers of forest with a rock that never even reached the ground. The cosmic lottery operates on its own schedule, independent of human civilization, politics, or preparedness. Every day we survive without a major impact is essentially a win in a game where the stakes include human extinction. Right now, thousands of cosmic bullets are following paths that cross Earth's orbit. Astronomers have a special name for these threats: near-Earth objects, or NEOs. These space rocks follow elliptical paths around the Sun, occasionally swinging close to Earth's orbital neighborhood. Some pass harmlessly by at safe distances. Others follow trajectories that could eventually intersect with Earth itself. The scary part: we've only discovered and tracked a fraction of them. Current estimates suggest over 25,000 asteroids larger than 140 meters cross Earth's orbital path. That's big enough to destroy entire metropolitan areas. Of these thousands of potential city killers, astronomers have located and tracked only about half. The other half remain completely unknown, invisible threats lurking in the darkness of space. Even more concerning, new NEOs regularly join this cosmic shooting gallery. Gravitational interactions with planets can nudge previously safe asteroids onto Earth-crossing orbits. What was harmless yesterday could become a threat tomorrow. We're essentially living in a cosmic neighborhood where thousands of loaded weapons are constantly changing their aim. Most will miss, but basic probability suggests that eventually one will. The most dangerous asteroids are often the ones we discover too late. Our cosmic early warning system has massive blind spots. Every month, astronomers discover new asteroids that have already passed closer to Earth than the Moon. Some of these cosmic near misses are large enough to devastate entire regions, yet they remain invisible until they're almost on top of us. By the time we spot them, deflection becomes impossible. There simply isn't enough time to mount any defense. The problem gets worse with smaller asteroids. Rocks large enough to level cities, but too small for our best telescopes to track regularly. These stealth threats can approach from the direction of the Sun, where our instruments are effectively blind. Others have dark surfaces that reflect almost no light, making them nearly invisible against the blackness of space. Even known asteroids can surprise us. Their orbits change slightly over time due to complex gravitational influences from planets, the Sun, and even the pressure of sunlight itself. An asteroid calculated to miss Earth by millions of kilometers could be nudged onto a collision course by forces we can barely measure. Our current tracking systems excel at finding the largest, most obvious threats. But the asteroid that actually hits us will likely be one we never saw coming until it was far too late to stop. Today's interconnected world is more fragile than any previous civilization. A single asteroid impact could trigger a cascade of failures that brings down modern society entirely. Our ancestors lived in small, isolated communities that could survive independently. Modern civilization operates as a single, integrated system where distant disasters become everyone's problem. A major asteroid impact anywhere on Earth would disrupt global supply chains, crash financial markets, and overwhelm communication networks worldwide. Consider what happens when a city destroyer asteroid hits a major port or manufacturing center. Global trade grinds to a halt. Supply chains for everything from computer chips to medical supplies collapse. Food distribution systems fail as transportation networks become overwhelmed with refugees and emergency responders. Our dependence on electricity makes everything worse. Modern asteroid impacts would likely trigger massive power grid failures through electromagnetic effects and physical damage. Without electricity, hospitals shut down, water treatment plants stop working, and entire cities become uninhabitable within days. The same technological advances that made us powerful also made us vulnerable. Satellite communications, GPS navigation, and internet infrastructure could all be disrupted by the atmospheric effects of major impacts. A civilization that can split atoms and explore Mars could be brought to its knees by a rock from space. For the first time in Earth's history, a species has the potential to protect itself from asteroid impacts. The question is whether we'll build those defenses before we need them. Every major asteroid impact in Earth's past happened to a planet that couldn't fight back. Dinosaurs, trilobites, and countless other species simply endured whatever the cosmos threw at them. Extinction was the only option when the sky started falling. Humans represent something new in Earth's 4.6 billion year history. Intelligence capable of detecting threats and technology powerful enough to deflect them. We can build telescopes to spot incoming asteroids decades in advance. We can design spacecraft to nudge threatening rocks onto safer paths. We can potentially prevent the next mass extinction. The capabilities exist, but only if we choose to develop them. Planetary defense requires international cooperation, sustained funding, and long-term thinking that extends beyond normal political cycles. We need early warning systems, deflection technologies, and response protocols ready before the next serious threat appears. This isn't science fiction. It's an engineering problem with known solutions. The only question is whether human civilization will invest in planetary defense before we face an asteroid with our name on it. Our survival as a species may depend on building humanity's cosmic shield before we discover we needed it yesterday. Every clear night, automated telescopes wake up and begin hunting for humanity's destroyers. These robotic sentries don't need human operators. They methodically photograph the same patches of sky over and over, searching for anything that moves. The strategy sounds simple but requires incredible precision. The telescopes capture multiple images of the same star field minutes apart. Computer software then compares these images, looking for tiny dots that have shifted position against the background of stationary stars. Most moving objects turn out to be harmless, distant comets or asteroids that pose no threat to Earth. But occasionally the computers flag something disturbing. A dot that's moving too fast, heading in the wrong direction, or following a path that could intersect Earth's orbit. When this happens, The automated system sends an alert to human astronomers who begin the urgent work of determining whether we're looking at our next cosmic executioner. These ground-based surveys have discovered over 90% of the large asteroids that could end human civilization. The robotic guardians work tirelessly, scanning millions of stars each night because they know that our survival depends on seeing death coming from space before it arrives. The U.S. Air Force built a system to track enemy satellites. Instead, it became our first line of defense against cosmic annihilation, LNR, which stands for Lincoln Near-Earth Asteroid Research. Started as a Cold War project designed to monitor threatening objects in Earth's orbit. Military engineers needed to know if enemy nations were launching spy satellites or space-based weapons. They created an automated system with powerful telescopes and sophisticated tracking software. Then someone realized the system could do something far more important than tracking human threats. It could hunt for natural ones. In the late 1990s, LNR began scanning for asteroids instead of satellites. The results were startling. LNR discovered over 2,000 potentially dangerous asteroids in its first decade of operation. Many of these space rocks had been silently stalking Earth for millions of years, completely unknown to human science. Some passed closer to Earth than the Moon on regular schedules we never knew existed. A military system designed to protect America from human enemies became humanity's early warning system against the universe itself. Sometimes the most important discoveries happen when you're looking for something else entirely. High in Arizona's desert mountains, a single telescope has found more Earth-threatening asteroids than any other instrument in human history. The Catalina Sky Survey operates from the University of Arizona, but its mission extends far beyond academic research. It's actively hunting for objects that could end civilization. The survey uses a 1.5-meter telescope that might seem modest compared to massive observatory instruments. But size isn't everything in asteroid hunting. What matters is speed, automation, and relentless consistency. Every clear night, Catalina's telescope captures hundreds of images covering vast sections of sky. The system processes these images using specialized software that can detect asteroids as faint as 21st magnitude, roughly 4 million times dimmer than stars visible to the naked eye. Most of these cosmic shadows remain completely invisible to human eyes, detectable only through the patient accumulation of photons over long exposures. Since 2005, Catalina has discovered over 7,000 near-Earth asteroids, including hundreds classified as potentially hazardous objects. Each discovery represents a cosmic threat that was previously unknown, lurking in the darkness until Catalina's mechanical eye spotted its telltale motion against the stars. One observatory in the Arizona desert has probably done more to secure humanity's future than most nations' entire defense budgets. Sometimes survival depends on a few dedicated people with the right tools watching the right patch of sky. Some of our most dangerous cosmic enemies remain invisible to ground-based telescopes. They're too dark, too distant, or positioned where Earth's atmosphere blocks our view. That's where an EOWASI comes in, a space telescope specifically designed to hunt what we can't see from the ground. EOWASI operates in infrared light, detecting heat instead of visible reflected sunlight. This capability proves crucial because many asteroids are essentially black rocks that reflect almost no light. They're virtually invisible to optical telescopes, but glow brightly in infrared due to heat absorbed from the sun. The telescope orbits Earth every 95 minutes, continuously scanning space while avoiding the sun's blinding glare. Its infrared sensors can detect asteroids that would be impossible to spot using traditional methods. Dark asteroids. Asteroids hiding in the sun's direction, asteroids too small for ground telescopes. NUBIA-C finds them all. Since beginning its asteroid hunting mission in 2013, NUBIA-C has discovered over 3,000 near-Earth objects and characterized the sizes and compositions of tens of thousands more. Many of these discoveries were completely unknown threats that could have surprised us with devastating results. Space-based infrared detection has revealed that the cosmic shooting gallery surrounding Earth is far more crowded than we ever realized from ground-based observations alone. Finding asteroids among millions of stars requires superhuman pattern recognition. Fortunately, we don't need humans to do the looking. We've taught computers to spot cosmic threats faster and more accurately than any human eye. The challenge seems straightforward until you consider the scale. A single night's asteroid survey might capture thousands of images containing billions of individual stars. Hidden among these stellar multitudes are perhaps a few dozen moving objects, most smaller than individual pixels. Human astronomers would need lifetimes to examine what computers process in minutes. Modern asteroid detection software works by taking multiple images of the same sky region spaced minutes apart. The computer then blinks between these images, looking for anything that changes position. Stars remain perfectly stationary while asteroids betray themselves through motion. The software can detect movement as small as 1/1000th of a degree across the sky. Advanced algorithms filter out false positives caused by cosmic rays, satellite trails, and image defects. They distinguish between different types of moving objects: near-Earth asteroids, main belt asteroids, comets, and artificial satellites. The most sophisticated systems can even estimate an object's distance and speed based purely on how it moves between images. Computer vision has transformed asteroid hunting from a tedious manual process into an automated early warning system that never sleeps, never blinks, and never misses a potentially threatening object moving through our cosmic neighborhood. Spotting a moving dot in space is just the beginning. The real challenge is determining where that dot is going and whether it might be heading for Earth. Calculating an asteroid's orbit requires a minimum of 3 observations spread across several nights. Each observation provides a snapshot of the object's position at a specific time. Astronomers feed these data points into complex mathematical models that trace the asteroid's path backward and forward through time. The process reveals everything we need to know about the threat level. The orbit calculation shows how close the asteroid will come to Earth, when these approaches will occur, and whether any future encounters pose a collision risk. It also reveals the asteroid's size, rotation period, and composition based on how its brightness changes over time. But orbital calculations aren't perfect. Slight errors in observation, gravitational perturbations from planets, and even pressure from sunlight can gradually change an asteroid's path. What appears safe today might become threatening decades from now. Astronomers must continuously refine their calculations as they gather more observations. This mathematical detective work transforms random dots of light into comprehensive threat assessments. The difference between 3 points of light and a complete orbital solution is often the difference between ignorance and survival. When a threatening asteroid approaches within a few million kilometers of Earth, astronomers deploy their most powerful investigative tool: planetary radar. These systems bounce radio waves off asteroids and analyze the echoes to reveal secrets that optical telescopes simply cannot detect. Radar penetrates an asteroid's surface, revealing internal structure, composition, and hidden characteristics that could determine how deadly an impact might be. Is the asteroid a solid chunk of rock that would survive atmospheric entry intact? Or a loose pile of rubble that might break apart harmlessly? Radar answers these critical questions. The Arecibo Observatory in Puerto Rico and the Goldstone Deep Space Communications Complex in California serve as humanity's primary radar eyes. When they focus on an approaching asteroid, radio waves travel millions of kilometers through space, strike the target, and return with detailed information about size, shape, rotation, and surface properties. Radar mapping can reveal asteroids that are actually binary systems, two objects orbiting each other. It can detect tumbling motion that might cause an asteroid to break apart during atmospheric entry. Most importantly, radar provides precise measurements that dramatically improve orbital predictions. These radio investigations have revealed that many asteroids are far stranger and more complex than simple space rocks. Understanding their true nature could mean the difference between a successful deflection mission and a catastrophic failure when we finally need to defend our planet. Protecting Earth from asteroid impacts requires something unprecedented in human history: genuine global cooperation with no room for competition, secrecy, or national advantage. The challenge is fundamentally geographical. Earth rotates every 24 hours, which means any single observatory can only monitor threats for roughly half the time. Asteroids approaching from the Sun's direction remain invisible to that hemisphere's telescopes. Weather equipment failures and maintenance downtime create additional blind spots that could prove fatal. The solution emerged gradually as observatories worldwide began sharing data in real time. The European Space Agency's Space Situational Awareness Program, NASA's Planetary Defense Coordination Office, and observatories from Australia to Chile now operate as a unified early warning network. When one facility loses track of a threatening object, another picks up the surveillance. This cooperation extends beyond simple data sharing. International protocols now exist for verifying potential threats, coordinating observations, and sharing the computational burden of orbital calculations. The Minor Planet Center in Massachusetts serves as a global clearinghouse, collecting observations from around the world and publishing definitive orbital information. Planetary defense has created something unique in international relations: a shared mission where failure anywhere threatens everyone equally. When faced with cosmic threats, national boundaries become meaningless abstractions. Not all asteroids pose equal threats to human civilization. Scientists have developed classification systems that separate cosmic nuisances from genuine extinction-level dangers. Size categories determine potential impact effects. Objects smaller than 25 meters typically burn up in Earth's atmosphere, creating spectacular fireballs but causing little surface damage. The 25 to 140 meter range can destroy cities if they hit populated areas but won't cause global effects. Asteroids larger than 140 meters become potentially hazardous objects capable of regional devastation. The truly civilization-threatening asteroids measure larger than 1 kilometer across. These monsters could trigger global climate effects, crop failures, and economic collapse even if they don't directly hit populated areas. Only about 1,000 such objects are known to cross Earth's orbit, and astronomers believe they found roughly 90% of them. Composition matters as much as size. Metallic asteroids survive atmospheric entry better than rocky ones, delivering more energy to the surface. Rubble pile asteroids might break apart harmlessly during atmospheric transit, while solid chunks of iron or stone punch through to create massive craters. Scientists also classify asteroids by orbital characteristics. Objects that make frequent close approaches to Earth pose higher statistical risks than those on more distant paths. The classification system helps prioritize which asteroids need continuous monitoring and which deserve immediate attention for possible deflection missions. Ground-based asteroid detection has reached its practical limits. The next generation of planetary defense will move beyond Earth's atmosphere to gain complete awareness of our cosmic environment. Several space-based survey missions are in development, designed to overcome the fundamental limitations of ground-based observations. The INEO Surveyor mission, scheduled for launch in the mid-2020s, will operate as a dedicated space-based infrared telescope optimized for asteroid detection. Unlike ground-based surveys limited by weather, atmospheric interference, and daylight, space-based systems can operate continuously. These orbital sentries will detect asteroids currently invisible to Earth-based telescopes. Objects approaching from the Sun's direction, dark asteroids with low reflectivity, and smaller objects that pose regional threats. Advanced space telescopes could provide decades of early warning for threats that current systems might only detect months before impact. The ultimate goal is complete situational awareness, a comprehensive catalog of every object larger than 30 meters that could potentially threaten Earth. This census would eliminate the element of surprise that makes asteroid impacts so dangerous. Future space surveillance networks will transform planetary defense from reactive threat response to proactive threat management. Instead of hoping we'll spot dangerous asteroids in time, we'll know exactly what's coming and have decades to prepare our response. Isaac Newton discovered the force that will determine whether humanity survives the next century. He called it gravity, and it controls every asteroid that threatens Earth. Newton's law sounds deceptively simple. Every object with mass attracts every other object with mass. The strength of this attraction depends on how massive the objects are and how far apart they sit. Bigger objects pull harder. Closer objects pull stronger, double the distance, and the gravitational force drops by 4 times. This mathematical relationship governs the motion of every threatening asteroid in our solar system. The Sun's massive gravity keeps asteroids orbiting in predictable patterns. Earth's gravity determines whether an approaching space rock will miss us, graze our atmosphere, or slam directly into our surface. Understanding gravitational forces allows scientists to calculate exactly where any asteroid will be at any future time. We can predict cosmic collisions decades in advance because gravity follows Newton's unchanging mathematical rules. The same law that makes apples fall from trees also controls the trajectories of civilization-ending space rocks. Every successful planetary defense mission will ultimately depend on calculations based on a law discovered by a 17th century mathematician who never imagined humanity would need to deflect asteroids to survive. Johannes Kepler revealed that asteroids and planets follow identical cosmic rules. They all travel in elliptical orbits around the Sun, like cosmic racer tracks with predictable speeds and schedules. Kepler's laws describe 3 fundamental patterns that govern all orbital motion. First, every orbit forms an ellipse, a stretched circle with the Sun positioned at one focus point. Second, objects move faster when closer to the Sun and slower when farther away. Third, the time required to complete one orbit depends entirely on the orbit's average distance from the Sun. These patterns mean that asteroid orbits are completely predictable once you know their basic characteristics. An asteroid's path through space follows mathematical precision that makes clockwork seem chaotic by comparison. Given enough observations, astronomers can calculate exactly where any asteroid will be at any time in the future. This predictability creates both opportunity and responsibility for planetary defense. We can forecast dangerous approaches decades in advance, providing ample time to plan deflection missions. But the same mathematical certainty means that if we calculate a future collision, it will happen exactly as predicted unless we take action to change the asteroid's orbit. Kepler's 400-year-old discoveries provide the foundation for every modern asteroid tracking system and every future mission to save Earth from cosmic impact. Asteroid orbits aren't as perfectly predictable as Kepler's laws suggest. Invisible gravitational influences constantly nudge these space rocks into slightly different paths, creating uncertainty that could mean the difference between impact and near miss. Every planet in our solar system tugs on passing asteroids with its gravitational field. Jupiter, with its massive size, exerts the strongest influence and can dramatically alter asteroid trajectories over time. Mars, Earth, Venus, and even smaller objects contribute their own gravitational pulls. These combined influences, called perturbations, slowly modify orbital paths in ways that become significant over decades or centuries. The challenge for asteroid tracking lies in calculating all these overlapping gravitational effects simultaneously. Scientists must account for the positions and masses of every significant object in the solar system to accurately predict where a threatening asteroid will be in the future. Small errors in these calculations can lead to huge uncertainties about collision timing and location. Modern computers handle millions of gravitational calculations to model how planetary perturbations affect asteroid orbits. But even the most sophisticated models contain uncertainties that grow larger the further we try to predict into the future. These invisible forces transform asteroid prediction from simple mathematical certainty into complex probability calculations where small errors today can determine whether civilization survives tomorrow. Sunlight doesn't just illuminate asteroids. It actually pushes them around in space through a subtle effect that can gradually change their orbits over millions of years. The Yarkovsky effect works because asteroids absorb sunlight on their sun-facing sides and radiate heat from their entire surfaces. As an asteroid rotates, its afternoon side becomes warmer than its morning side. This creates a tiny temperature difference that produces a small thrust, like an extremely weak rocket engine that never shuts off. The force generated is incredibly small, roughly equivalent to the pressure you'd feel from a feather resting on your hand. But in the vacuum of space, even tiny forces can produce significant effects over long time periods. After millions of years, Yarkovsky thrust can move an asteroid into a completely different orbit. This effect poses serious challenges for long-term asteroid prediction. An asteroid calculated to miss Earth by millions of kilometers might slowly drift into a collision course due to accumulated Yarkovsky push over centuries. Conversely, a threatening object might naturally drift away from Earth without any human intervention. Understanding thermal forces helps scientists refine their orbital predictions and identify asteroids whose paths might change significantly over time. Sometimes the sun itself provides the gentle push needed to nudge dangerous objects away from Earth. Astronomers have a specific term for cosmic near misses that make them lose sleep: close approaches. These events occur when asteroids pass within a few million kilometers of Earth, uncomfortably close by astronomical standards. A close approach in asteroid terms means the object passes within about 30 times the distance between Earth and the Moon. While this might sound safely distant, it represents the cosmic equivalent of a bullet passing just centimeters from your head. At these distances, gravitational interactions between Earth and the asteroid become significant and can alter future orbital paths. Each close approach creates an opportunity for more precise tracking and characterization. As asteroids pass nearby, ground-based radar systems can map their surfaces, determine their rotation rates, and measure their exact sizes. These observations dramatically improve scientists' ability to predict where the object will go next. But close approaches also create anxiety because they represent potential collision opportunities. An asteroid that passes harmlessly this time might return on a slightly different path that brings it even closer during its next approach. The orbital changes caused by gravitational interactions during close encounters can be difficult to predict precisely. Every close approach serves as both a scientific opportunity and a reminder that we live in a cosmic shooting gallery where the bullets regularly pass close enough to feel the wind. Predicting asteroid collisions isn't about certainty. It's about calculating probabilities that help humanity make life or death decisions. Orbital calculations always contain uncertainties due to measurement errors, gravitational perturbations, and effects like thermal pressure from sunlight, instead of declaring that an asteroid will definitely hit or miss Earth. Scientists calculate probability distributions that show the range of possible outcomes and their relative likelihood. These calculations use a technique called Monte Carlo simulation, which runs thousands of different orbital scenarios based on slightly different initial conditions. Each simulation represents a possible version of reality consistent with our observational uncertainties. If 50 out of 10,000 simulations result in Earth impact, the collision probability is roughly 0.5%. Scientists consider any probability above 1 in a million worthy of continued monitoring. Probabilities above 1 in 1,000 trigger serious consideration of deflection missions. Anything approaching 1 in 100 demands immediate action, regardless of cost or technical challenges. These mathematical analyses transform vague notions of cosmic risk into precise calculations that governments and space agencies can use to make informed decisions about planetary defense investments. Probability calculations provide the scientific foundation for humanity's most important insurance policy. Some asteroid encounters with Earth create invisible traps in space that can turn harmless flybys into future collision courses. Astronomers call the cosmic snares gravitational keyholes. A keyhole represents a very small region of space, sometimes only a few hundred meters wide, where Earth's gravity can deflect a passing asteroid just enough to ensure it returns on a collision trajectory during a future close approach. If an asteroid passes through a keyhole during one encounter, it becomes almost guaranteed to hit Earth during a subsequent flyby. The most famous example involves asteroid Apophis, which will pass extremely close to Earth in 2029. Initial calculations suggested a small chance that Apophis might through a gravitational keyhole, ensuring impact during its 2036 return. Additional observations have since ruled out this scenario, but Apophis demonstrates how keyholes transform low-probability threats into high-probability disasters. Keyhole effects mean that some close approaches deserve more attention than others. An asteroid that misses the keyhole by a comfortable margin poses minimal future risk, but an object whose trajectory uncertainty overlaps with a keyhole region requires intensive monitoring and possible deflection efforts. These gravitational traps represent one of the most insidious aspects of asteroid threats. The possibility that a harmless close encounter today could set up an unavoidable collision decades from now. Scientists needed a simple way to communicate asteroid threats to the public without causing mass panic. They created the Torino scale, a color-coded system that ranks cosmic dangers from no big deal to kiss your civilization goodbye. The Torino scale runs from 0 to 10, with each number corresponding to a specific level of threat and appropriate public response. Level 0 represents objects with essentially zero collision probability or impacts too small to cause significant damage. These require no public attention. Level 1 indicates objects that deserve continued monitoring but pose no immediate concern. The scale jumps dramatically at higher levels. Level 4 represents a close encounter that poses a 1% or greater chance of regional devastation. Level 7 indicates a likely collision capable of causing regional destruction. Level 8 means a certain collision that could cause regional destruction or global climate effects. Levels 9 and 10 represent civilization-ending scenarios. Level 9 indicates certain collision with regional destruction and possible global catastrophe. Level 10, the red zone, means certain collision capable of causing global climatic catastrophe and threatening the survival of civilization as we know it. No asteroid has ever been assigned a Torino scale rating above 4, and most of those have since been downgraded to 0 as additional observations refine their orbital predictions. While the Torino scale communicates asteroid risks to the public, scientists use a more sophisticated system called the Palermo scale to make technical decisions about resource allocation and mission planning. The Palermo scale compares the collision probability of a specific asteroid against the background risk from all asteroids of similar size. A Palermo value of 0 means the object poses exactly average risk for its size category. Negative values indicate below average risk. Positive values signal above average concern. This relative approach helps scientists prioritize threats more effectively than simple probability calculations alone. An asteroid with a 1 in 10,000 collision probability might seem alarming, but if similar-sized objects typically pose 1 in 1,000 risks, this particular asteroid actually deserves less attention than average. The Palermo scale accounts for both collision probability and the time until potential impact. Threats that could occur within decades receive higher priority than identical risks centuries in the future. This temporal weighting ensures that limited planetary defense resources focus on the most pressing dangers. Values above +2 on the Palermo scale indicate objects that deserve serious consideration for deflection missions. The highest Palermo values ever calculated for known asteroids reach only about +1.9, suggesting that while significant threats exist, none currently qualify as immediate civilization-ending emergencies. The biggest challenge in asteroid threat assessment comes from a fundamental limitation. We often must make critical decisions based on just a few nights of telescope observations. When astronomers first discover a new asteroid, they can only observe it for a brief period before it moves too far away for detailed tracking. This observation arch, the period over which they can measure the object's position, might last only days or weeks. Yet scientists must use these limited data points to predict the asteroid's behavior over decades or centuries. Short observation arcs create enormous uncertainties in long-term orbital predictions. An asteroid observed for only 3 nights might have an orbital uncertainty so large that scientists can't determine whether it will miss Earth by millions of kilometers or score a direct hit during its next close approach. The uncertainty problem compounds over time. Small errors in initial orbital calculations grow exponentially larger when projected far into the future. An asteroid whose position uncertainty spans a few thousand kilometers today might have location uncertainty spanning millions of kilometers when predicting its position decades from now. This fundamental limitation means that newly discovered asteroids often trigger initial alerts that are later canceled as additional observations refine their orbital predictions. The observation arc problem forces scientists to balance rapid threat assessment against the reality that their initial calculations may be wildly inaccurate. Once scientists calculate that an asteroid might hit Earth, they face an even more challenging task: predicting exactly what will happen when it arrives. Impact scenario modeling combines orbital mechanics with atmospheric physics, geology, and climate science to forecast the complete sequence of events during an asteroid collision. These analyses determine where the object will hit, how much energy it will release, what types of damage will occur, and how far the effects will spread. The calculations consider dozens of variables that affect impact consequences. Asteroid composition determines how much energy reaches the ground versus being absorbed by the atmosphere. Impact angle affects the distribution of debris and shock waves. Impact location, whether ocean or land, populated or remote, determines human casualties and economic damage. Advanced computer models simulate the entire impact sequence from atmospheric entry through long-term climate effects. They calculate blast radii, tsunami heights, debris distributions, and atmospheric dust loading that could trigger impact winter conditions. These simulations provide emergency planners with specific information about evacuation zones, expected casualties, and regional damage patterns. Impact scenario planning transforms abstract orbital mechanics into concrete preparations for survival. The mathematical precision that allows us to predict asteroid arrivals also enables detailed planning for managing the aftermath if our deflection efforts fail. The final step in asteroid threat assessment involves translating complex mathematical analysis into clear warnings that can trigger appropriate emergency responses worldwide. International warning systems operate through a carefully structured hierarchy designed to prevent both false alarms and delayed responses to genuine threats. Initial asteroid discoveries undergo rapid preliminary assessment to identify objects that might pose near-term collision risks. Confirmed threats trigger increasingly urgent alerts as collision probability and confidence levels increase. The warning timeline typically spans years or decades, providing ample time for deflection missions and emergency preparations. Level 1 alerts indicate objects requiring additional observations to clarify threat levels. Level 2 warnings signal probable threats that justify beginning deflection mission planning. Level 3 alerts confirm certain impacts and trigger full emergency response protocols. These systems balance the need for early warning against the dangers of premature alarms that could cause unnecessary panic or economic disruption. Warning protocols include specific procedures for coordinating international responses, managing public communications, and ensuring that critical information reaches decision-makers who can authorize planetary defense missions. Modern asteroid warning systems represent humanity's first attempt to create a global early warning network for existential threats. When the next serious asteroid threat emerges, these protocols will determine whether our species receives adequate warning to mount an effective defense. Mass creates an invisible force that reaches across the emptiness of space. This fundamental principle, that every object with mass attracts every other object with mass, provides the foundation for humanity's gentlest method of asteroid deflection. The gravitational force between two objects depends on their masses and the distance separating them. Heavier objects create stronger gravitational fields. Closer objects experience stronger attractive forces. Double the mass of either object, and the gravitational pull doubles. Double the distance between them, and the force drops to 1/4 its original strength. This universal attraction works both ways simultaneously. Earth pulls on the Moon, but the Moon also pulls back on Earth with equal force. A spacecraft orbiting an asteroid experiences gravitational attraction toward the space rock, but the asteroid experiences an equal and opposite pull toward the spacecraft. Understanding this mutual attraction reveals how gravity tractor deflection works. A massive spacecraft positioned near a threatening asteroid creates a tiny but persistent gravitational pull that slowly tugs the space rock into a safer orbit. The method harnesses the same force that holds planets in orbit around the Sun. Gravitational interaction provides a cosmic towing service that works across vacuum without any physical contact, cables, or mechanical connections between the towing vehicle and its target. The key to gravity tractor deflection lies in a counterintuitive strategy: park a heavy spacecraft near an asteroid and let physics do the work. A gravity tractor operates by positioning a massive spacecraft, typically weighing several tons, at a precise distance from the target asteroid. The spacecraft's gravitational field creates a weak but constant force that pulls on the asteroid's entire mass. This invisible tether works like an extremely gentle cosmic tugboat that never stops pulling. The deflection force remains incredibly small, roughly equivalent to the gravitational pull between two cars parked 100 meters apart. But in the frictionless environment of space, even tiny forces can produce significant effects when applied continuously over years. The accumulated effect gradually shifts the asteroid's velocity just enough to change its orbital path. Success depends entirely on the spacecraft's mass. A heavier gravity tractor generates stronger gravitational pull and produces faster deflection. Mission planners often design these spacecraft to be much more massive than typical scientific probes, sometimes including dense materials like tungsten or lead to maximize gravitational effectiveness without increasing size. The spacecraft mass effect transforms gravitational attraction from a cosmic curiosity into a practical tool for planetary defense, turning Newton's law of universal gravitation into humanity's shield against asteroid impacts. Operating a gravity tractor requires maintaining an exact position relative to a tumbling, irregularly shaped asteroid, while both objects hurtle through space at thousands of kilometers per hour. The spacecraft must hover at the optimal distance, where its gravitational pull maximizes deflection efficiency without risking collision with the asteroid. Too close, and the spacecraft might crash into surface features or be captured into an unstable orbit around the asteroid. Too far away, and the gravitational force becomes too weak to produce meaningful deflection. This optimal position typically lies somewhere between a few hundred meters and several kilometers from the asteroid's surface, depending on the size and mass of both objects. The exact distance requires complex calculations that account for the asteroid's irregular gravitational field, rotation rate, and surface features that might interfere with spacecraft operations. Maintaining position becomes even more challenging because asteroids often tumble chaotically through space rather than rotating smoothly like planets. The spacecraft must constantly adjust its position to compensate for the asteroid's changing orientation and the varying strength of gravitational attraction as different parts of the irregularly shaped object come closer or farther away. Precision position control transformed gravity tractor operations from a simple concept into one of the most demanding spacecraft operations ever attempted, requiring autonomous navigation systems that can respond to changing conditions in real time. Chemical rockets lack the endurance needed for gravity tractor missions. The solution comes from ion engines, electric propulsion systems that can operate continuously for years while consuming minimal fuel. Propulsion works by accelerating electrically charged particles to extremely high speeds and ejecting them as exhaust. These engines produce thrust levels measured in millinewtons, roughly equivalent to the weight of a piece of paper resting on your hand, but they can maintain this gentle push for months or years without running out of fuel. The low thrust perfectly matches gravity tractor requirements. The spacecraft needs just enough power to counteract the asteroid's weak gravitational pull while maintaining its position and gradually nudging the space rock onto a safer trajectory. Chemical rockets would exhaust their fuel supplies within days or weeks of such operations. Engines derive their power from solar panels or nuclear generators, converting electrical energy into kinetic energy with incredible efficiency. They can achieve fuel economy roughly 10 times better than the best chemical rockets, making multi-year deflection missions economically feasible. These electric propulsion systems transform gravity tractors from theoretical concepts into practical spacecraft that can perform the extended operations necessary to deflect threatening asteroids through gentle gravitational persuasion rather than violent collision. Saving civilization from asteroid impact requires patience. Gravity tractor missions operate on timescales measured in years because changing an asteroid's orbit demands accumulated momentum over extended periods. The physics of orbital mechanics works against rapid deflection attempts. A small change in an asteroid's velocity, measured in centimeters per second, can translate into thousands of kilometers of positional difference when the object reaches Earth's vicinity years later. But achieving even these tiny velocity changes through gravitational towing requires months or years of continuous operation. Consider deflecting a 300-meter asteroid discovered 20 years before potential impact. A gravity tractor might need to operate for 5 years to accumulate enough orbital change to ensure the asteroid misses Earth by a comfortable margin. Shorter mission durations would require more massive spacecraft or multiple gravity tractors working simultaneously. The extended timeline actually works in humanity's favor by providing multiple opportunities to refine deflection efforts. Mission controllers can continuously monitor the asteroid's changing trajectory and adjust spacecraft operations to ensure optimal deflection. They can even abort the mission if new calculations show the threat was miscalculated. Long-duration operations transform asteroid deflection from a desperate last-minute intervention into a carefully managed, multi-year project that provides ample time for course corrections and contingency planning. Unlike explosive deflection techniques that risk breaking asteroids into multiple dangerous fragments, gravity tractor systems move threatening objects intact and undamaged. The gentle approach addresses one of the fundamental risks of more aggressive deflection methods. Explosive techniques or high-velocity impacts might shatter a large asteroid into dozens of smaller pieces, potentially creating a swarm of city-killer objects where previously only one civilization-threatening rock existed. Gravity tractors avoid this fragmentation problem entirely. The method works by applying force to the asteroid's entire mass simultaneously rather than concentrating energy at a single impact point. This distributed approach ensures that internal stresses remain below the breaking threshold for even the most fragile space rocks. Asteroids that might disintegrate under impact remain completely stable under gravitational influence. Maintaining structural integrity also preserves the predictability of deflection efforts. An intact asteroid follows calculable orbital mechanics, allowing mission planners to predict exactly where it will go after deflection. Fragmenting an asteroid creates multiple unpredictable objects whose individual trajectories become nearly impossible to forecast accurately. The gentle method represents the most conservative approach to planetary defense, guaranteed to reduce rather than multiply the number of threatening objects while preserving our ability to predict and verify successful deflection outcomes. Gravity tractors must account for tidal forces, the same phenomenon that causes ocean tides on Earth. When positioning themselves near target asteroids, tidal effects occur because gravitational force varies with distance. The site of an asteroid closest to the gravity tractor spacecraft experiences slightly stronger gravitational pull than the far side. This difference creates internal stresses within the asteroid that could potentially cause it to break apart or alter its rotation in unpredictable ways. The challenge becomes more complex when dealing with asteroids that are actually loose collections of rubble held together by weak gravitational attraction. These rubble pile asteroids might disintegrate if tidal forces from the gravity tractor exceed the weak internal gravity, keeping the debris consolidated. Loss of structural integrity would scatter the asteroid into unpredictable fragments. Mission planners minimize tidal effects by carefully selecting spacecraft positioning and mass distribution. The optimal location balances deflection efficiency against tidal stress limits, ensuring maximum gravitational influence without exceeding the asteroid's structural tolerance. Advanced mission designs might use multiple smaller spacecraft rather than one massive tractor to distribute tidal effects more evenly. Understanding and managing tidal forces ensures that gravity tractor operations enhance rather than compromise planetary safety by preventing the accidental creation of multiple threatening fragments from a single manageable target. The largest and most dangerous asteroids require more gravitational muscle than a single spacecraft can provide. The solution involves coordinating multiple gravity tractors in formation flying operations. Multiple spacecraft can generate combined gravitational forces that exceed what any single vehicle could achieve within reasonable mass and cost constraints. A formation of 3 to 5 gravity tractors can deflect asteroids that would be completely unmanageable using single spacecraft operations. The combined approach also provides redundancy. If one spacecraft fails, the others continue deflection operations. Coordination between multiple spacecraft creates new challenges that single vehicle operations avoid. Each gravity tractor must maintain precise positioning not only relative to the asteroid, but also relative to its partner spacecraft. The gravitational fields of the spacecraft themselves can interfere with each other, creating complex orbital dynamics that require sophisticated navigation systems. Formation flying operations also multiply the complexity of mission planning and control. Ground controllers must monitor and adjust the trajectories of multiple spacecraft simultaneously, while ensuring that their combined gravitational effects produce the desired deflection without unwanted side effects like induced asteroid rotation or structural stress. Multiple gravity tractors represent the heavy artillery of gentle deflection methods, capable of moving even the largest threatening asteroids, while maintaining the safety advantages of non-destructive techniques. The vast distances and communication delays of deep space operations make human control of gravity tractor missions impractical. Artificial intelligence systems must pilot these spacecraft autonomously while making split-second decisions that determine humanity's survival. Communication signals between Earth and asteroid locations can take anywhere from several minutes to over an hour to travel each direction. By the time ground controllers receive information about a spacecraft malfunction or navigation error, the situation may have already become catastrophic. Autonomous systems must detect and respond to problems within seconds or minutes rather than hours. AI navigation systems continuously monitor the asteroid's position, rotation, and gravitational field while adjusting spacecraft trajectory to maintain optimal deflection geometry. These systems must recognize and respond to unexpected changes in the asteroid's behavior, such as outgassing that could alter its rotation or surface features that create local gravitational anomalies. The artificial intelligence must also manage spacecraft resources autonomously, optimizing power consumption, fuel usage, and equipment operation throughout multi-year missions. It needs to diagnose and compensate for equipment failures, recalculate mission parameters when conditions change, and even abort operations if continuing the mission would create greater risks than the asteroid impact itself. Autonomous navigation transforms gravity tractor spacecraft into independent robotic agents capable of making complex decisions about planetary defense without waiting for human approval from Earth. Gravity tractor missions demand fuel efficiency that chemical propulsion simply cannot provide. Electric propulsion systems achieve fuel economy levels that make multi-year deflection missions economically feasible. Chemical rockets burn fuel rapidly to produce high thrust levels suitable for quick maneuvers, but gravity tractor operations require exactly the opposite performance profile. Low thrust maintained continuously over months or years. Chemical systems would exhaust their fuel supplies long before achieving meaningful deflection results. Propulsion systems achieve specific impulse values, a measure of fuel efficiency, roughly 10 times higher than the best chemical rockets. This means an ion-powered gravity tractor can operate 10 times longer on the same amount of fuel, or achieve the same operational duration using 1/10 the fuel mass. The efficiency advantage becomes crucial for asteroid deflection missions launched on relatively small rockets. Limited launch capacity forces mission designers to minimize spacecraft mass, including fuel supplies. Electric propulsion allows gravity tractors to pack enough operational capability into launch-constrained packages to accomplish their planetary defense mission. Fuel efficiency transforms gravity tractors from fuel-hungry spacecraft that require massive launch vehicles into compact, long-endurance systems that can reach threatening asteroids using existing launch infrastructure while carrying enough propellant to complete multi-year deflection operations. Before gravity tractor deflection becomes our cosmic insurance policy, engineers needed proof that spacecraft can operate precisely near asteroids. NASA's OSIRIS-REx mission provided exactly that validation. OSIRIS-REx spent over 2 years operating in close proximity to asteroid Bennu, maintaining precise positions just meters above the surface, while mapping every detail of the space rock structure and composition. The mission demonstrated that spacecraft can navigate safely around irregular, tumbling asteroids while avoiding collisions with unexpected surface features. The spacecraft successfully collected samples from Bennu's surface in 2020, proving that precise positioning and navigation systems can function reliably in the complex gravitational environment around small asteroids. These same navigation technologies form the foundation for future gravity tractor operations that will require even more precise positioning over much longer time periods. OSIRIS-REx also revealed crucial information about asteroid composition and structure that affects gravity tractor mission planning. The mission showed that many asteroids are loose collections of rubble rather than solid rocks, information that influences how gentle deflection methods should be applied to avoid structural damage. The technological success of OSIRIS-REx transformed gravity tractor concepts from theoretical proposals into validated engineering approaches ready for operational implementation when the next serious asteroid threat requires gentle deflection rather than destructive intervention. When two objects collide in space, they follow an unbreakable rule that governs everything from billiard balls to galaxies. This fundamental principle, called conservation of momentum, provides the scientific foundation for humanity's most direct method of asteroid deflection. Momentum equals mass multiplied by velocity. A bowling ball rolling slowly has the same momentum as a ping-pong ball traveling extremely fast. When objects collide, their combined momentum before impact exactly equals their combined momentum afterward. No momentum disappears or appears from nowhere. It simply transfers between objects. This conservation law works perfectly in the vacuum of space, where no friction or air resistance interferes with collisions. A spacecraft traveling at 10 kilometers per second carries enormous momentum despite its relatively small mass. When it strikes a much larger asteroid moving slowly, momentum transfers from the fast-moving spacecraft to the massive space rock. The mathematics are straightforward, but the implications are profound. A carefully aimed spacecraft impact can change an asteroid's velocity by the precise amount needed to shift its orbit away from Earth. The momentum transfer follows predictable physics that allows mission planners to calculate exactly how much deflection each impact will produce. Conservation of momentum transforms kinetic impact missions from random collisions into precision engineering projects where the laws of physics guarantee specific deflection results. September 26, 2022 marked the first time humanity deliberately changed the orbit of an asteroid, NASA's DART mission. The double asteroid redirection test successfully demonstrated that kinetic impactors can deflect threatening space rocks. DART targeted Morphos, a small asteroid orbiting a larger companion called Didymos. The spacecraft, roughly the size of a vending machine, traveled at 6.1 kilometers per second when it struck Dimorphos head-on. The collision occurred exactly as planned, with ground-based telescopes recording the precise moment of impact through dramatic changes in the asteroid system's brightness. The results exceeded expectations dramatically. Mission planners hoped the impact might change Dimorphos's orbital period by 10 minutes. The actual deflection measured 32 minutes, more than triple the minimum success threshold. The enhanced effectiveness came from debris ejected during impact that provided additional thrust beyond the spacecraft's momentum transfer. DART transformed kinetic impact deflection from theoretical concept into proven technology. The mission demonstrated that humans can hit fast-moving targets millions of kilometers away with sufficient precision to achieve measurable orbital changes. More importantly, it proved that kinetic impacts can deflect asteroids without breaking them apart into multiple dangerous fragments. This successful demonstration provides the technological foundation for operational planetary defense systems capable of protecting Earth from future asteroid threats. The angle of impact determines how efficiently a kinetic impactor transfers momentum to its target asteroid. Hitting from the wrong direction can waste most of the deflection potential or even accelerate the asteroid toward Earth. Maximum deflection efficiency occurs when the impactor strikes perpendicular to the asteroid's velocity vector, essentially hitting it from the side rather than head-on or from behind. This geometry ensures that all momentum transfer contributes directly to changing the asteroid's orbital velocity rather than just altering its position along the same orbit. Head-on collisions that oppose the asteroid's motion can slow it down, causing it to fall into a lower orbit that might actually increase collision probability with Earth. Rear impacts that push in the same direction as the asteroid's motion can accelerate it into higher orbits, but the deflection efficiency remains lower than optimal perpendicular impacts. The challenge lies in achieving precise impact geometry while accounting for the asteroid's rotation, irregular shape, and complex gravitational environment. Mission planners must calculate exact approach trajectories that deliver the impactor at precisely the right angle despite months or years of flight time through space. Impact angle optimization transforms kinetic deflection from simple collision mechanics into sophisticated orbital engineering that maximizes deflection effectiveness while minimizing the risk of accidentally worsening the threat. The deflection achieved by kinetic impact depends on the ratio between the impactor's mass and the target asteroid's mass. Even small spacecraft can produce meaningful deflection of much larger asteroids through the leverage of high-velocity impacts. A 500-kilogram spacecraft traveling at typical interplanetary speeds carries momentum equivalent to a freight train. When this momentum transfers to an asteroid millions of times more massive, the resulting velocity change appears tiny, perhaps only centimeters per second. But small velocity changes accumulate into enormous positional differences when projected across years of orbital motion. The mass ratio effect means that bigger impactors don't always produce proportionally better results. Doubling the spacecraft mass doubles the momentum transfer, but launching twice the mass might require larger rockets, longer travel times, or reduced accuracy. Mission designers must balance impactor size against operational constraints to optimize deflection per dollar spent. Multiple smaller impactors can sometimes achieve better results than single large ones. Sequential impacts allow mission controllers to observe and adjust targeting based on the effects of previous collisions. They also provide redundancy. If one impactor fails, others can complete the deflection mission. Understanding mass ratio effects allows planetary defense planners to design cost-effective deflection missions that achieve maximum orbital change using minimum spacecraft resources. Kinetic impacts don't just dent asteroid surfaces. They excavate massive craters while launching clouds of debris into space. This crater formation process significantly amplifies the deflection effects beyond simple momentum transfer. The impact sequence unfolds in microseconds but creates effects that last for hours. When the impactor strikes, it penetrates several meters into the asteroid's surface before its kinetic energy gets absorbed by crushing and heating rock. The energy deposition creates a shock wave that propagates outward, fracturing and accelerating surrounding material. The expanding shock wave excavates a crater roughly 10 to 20 times wider than the original impactor. Debris from this excavation process gets thrown outward at velocities ranging from a few meters per second to several kilometers per second. The fastest-moving ejecta escape the asteroid's weak gravitational field entirely and fly off into space. This debris ejection creates an additional source of momentum transfer that can double or triple the deflection effects compared to the original spacecraft impact alone. The asteroid experiences recoil from launching thousands of tons of rock into space, similar to the kick from firing a shotgun or launching a rocket. Crater formation transforms kinetic impactors from simple projectiles into excavation devices that harness the target asteroid's own material to amplify deflection effectiveness through natural rocket propulsion. Scientists discovered that kinetic impacts achieve far greater deflection than momentum conservation alone would predict. This enhancement effect, called the beta factor, can multiply deflection efficiency by factors of 2 to 5 depending on asteroid properties. The beta factor quantifies how much additional momentum transfer comes from debris ejected during crater formation. When high-velocity ejecta leaves the asteroid, it carries away momentum that must be balanced by equal and opposite momentum imparted to the remaining asteroid mass. This recoil effect supplements the original impactor momentum. Beta values depend on asteroid composition, impact velocity, and impactor design. Rocky asteroids with low-gravity wells tend to produce higher beta factors because more impact debris escapes entirely rather than falling back to the surface. Faster impacts generally create higher beta values by generating more energetic ejecta clouds. The DART mission achieved a beta factor of approximately 3.6, meaning the total momentum transfer was nearly 4 times greater than the spacecraft's original momentum alone. This enhancement explains why DART's deflection results exceeded predictions so dramatically. Understanding beta factor effects allows mission planners to design impactors that maximize ejecta production while ensuring the target asteroid remains structurally intact rather than fragmenting into multiple dangerous pieces. Hitting a small asteroid from millions of kilometers away requires navigation precision that exceeds the accuracy of any military weapon system ever built. Autonomous guidance systems must adjust spacecraft trajectories in real time to ensure collision occurs at exactly the right location. The targeting challenge combines multiple sources of uncertainty that compound over months of flight time. Asteroid positions predicted from ground-based observations contain errors that can accumulate into targeting misses of hundreds of kilometers. Spacecraft navigation errors, thruster performance variations, and gravitational perturbations from planets add additional uncertainties. Advanced impactor missions use autonomous navigation systems that can detect and track target asteroids during the final approach phase. These systems employ optical cameras and sophisticated image processing software to identify the target against the star-filled background of space. Real-time tracking allows the spacecraft to correct its trajectory continuously as it approaches. The final targeting phase typically begins when the spacecraft reaches within 100,000 kilometers of its target, close enough for onboard cameras to resolve the asteroid as more than a single pixel. From this point, autonomous systems take complete control of navigation and impact timing, adjusting the trajectory dozens of times during the final hours of flight. Precision targeting transforms kinetic impactor missions from ballistic projectiles into smart weapons capable of hitting fast-moving targets with accuracy measured in meters rather than kilometers. Successful kinetic deflection requires detailed knowledge of the target asteroid's properties that can only be obtained through advanced scouting missions. Blind impacts risk unexpected failures that could worsen rather than improve Earth's safety. Reconnaissance spacecraft must characterize the asteroid's mass, density, rotation state, and surface composition before impactor arrival. These properties determine optimal impact strategies, expected deflection efficiency, and structural integrity limits that define safe operation parameters. Attacking unknown targets could fragment loose rubble pile asteroids into dangerous debris swarms. Advanced exploration also identifies surface features that affect targeting accuracy. Large boulders, deep craters, or steep slopes near the planned impact site could interfere with navigation systems or redirect the impactor away from optimal collision geometry. Detailed surface mapping allows mission planners to select impact locations that maximize deflection while minimizing operational risks. The reconnaissance timeline typically requires 1 to 2 years for the Scout spacecraft to reach the target, conduct detailed observations, and transmit data back to Earth for analysis. This advance warning requirement means kinetic deflection missions need substantial lead time to achieve maximum effectiveness. Prior exploration transforms kinetic impact operations from desperate gambles into carefully planned surgical strikes that maximize success probability while minimizing unintended consequences. Confirming that kinetic impacts successfully deflected threatening asteroids requires precise measurements that can detect tiny orbital changes across vast cosmic distances. Ground-based telescopes and space-based observatories work together to verify deflection mission success. The measurement challenge stems from the enormous distances involved and the relatively small deflection effects produced. A successful impact might change an asteroid's orbital period by only minutes while the object remains millions of kilometers from Earth. Detecting these subtle changes requires observation precision that pushes astronomical instruments to their technical limits. Multiple measurement techniques provide independent verification of deflection results. Radar observations can detect changes in the asteroid's distance and velocity with centimeter-level accuracy. Optical telescopes track position changes against background star fields over time. Radio telescopes monitor variations in reflected signals that indicate orbital modifications. The verification timeline extends over weeks or months after impact as observers accumulate enough data to distinguish genuine orbital changes from normal measurement uncertainties. Initial results typically emerge within days, but final confirmation requires extended observations that rule out alternative explanations for apparent trajectory modifications. Effect verification transforms kinetic impact missions from one-shot experiments into quantified engineering demonstrations that provide precise data for designing future planetary defense operations. Some asteroid threats require multiple kinetic impacts spaced over months or years to accumulate sufficient deflection. Sequential impact strategies provide the capability to deflect massive asteroids that exceed single impact limitations. The sequential approach allows mission controllers to observe and analyze the effects of each impact before launching subsequent impactors. Early impacts provide real-time data about asteroid composition, structural integrity, and deflection efficiency that inform the design and targeting of follow-up missions. This adaptive strategy maximizes deflection effectiveness while minimizing the risk of accidental fragmentation. Timing coordination becomes critical when planning multiple impacts against rotating or tumbling asteroids. Each impactor must arrive when the target presents optimal impact geometry for maximum momentum transfer. Poor timing could result in impacts that cancel each other's deflection effects or strike the asteroid from angles that reduce overall efficiency. Sequential impacts also provide essential redundancy for planetary defense operations. Launch failures, navigation errors, or impactor malfunctions that doom individual missions don't necessarily compromise the overall deflection campaign. Backup impactors can compensate for individual failures while maintaining the accumulated deflection needed to ensure Earth's safety. The sequential impact strategy transforms kinetic deflection from single-shot interventions into sustained campaigns capable of deflecting even the largest civilization-threatening asteroids through coordinated precision strikes. Nuclear weapons represent the most powerful energy source humans have ever created. A single modern nuclear warhead releases more energy than every conventional explosive used in World War II combined. The energy output from nuclear fission or fusion reactions measures in megatons. Each megaton equals the explosive force of 1 million tons of TNT. Even relatively small nuclear devices produce yields measured in tens of kilotons, equivalent to 10,000 tons of conventional explosives. The largest nuclear weapons ever tested reached 50 megatons, creating fireballs several kilometers across. This incredible energy density makes nuclear weapons the only realistic option for deflecting massive asteroids discovered with little warning time. Chemical explosives and kinetic impact methods simply cannot deliver enough energy to change the trajectory of a kilometer-sized space rock approaching Earth. Nuclear energy provides the brute force necessary to alter the orbit of even the largest civilization-threatening asteroids. The physics of asteroid deflection favor high-energy solutions when time runs short. A nuclear explosion can deliver more momentum transfer in seconds than gentle deflection methods could achieve over years. When facing imminent cosmic collision, nuclear weapons transform from instruments of war into tools of species survival. Nuclear energy represents humanity's most powerful shield against asteroid impacts, providing orders of magnitude more deflection capability than any conventional alternative. Direct nuclear explosions on an asteroid's surface create thrust through a violent process of vaporization and ejection. The method transforms solid rock into high-velocity exhaust that pushes the remaining asteroid in the opposite direction. When a nuclear device detonates against an asteroid's surface, the intense heat and radiation instantly vaporize thousands of tons of rock and ice. This superheated material expands explosively away from the surface at speeds of several kilometers per second. The expanding vapor cloud acts like rocket exhaust, generating thrust through Newton's third law. For every action, there's an equal and opposite reaction. The explosion creates a shallow crater while simultaneously providing deflection impulse. The vaporized material carries away momentum that would otherwise remain with the asteroid, effectively reducing the object's mass while changing its velocity. Both effects contribute to orbital modification that can prevent Earth collision. Surface explosion efficiency depends on the asteroid's composition and structure. Rocky asteroids provide more material for vaporization than icy objects. Solid asteroids channel explosion energy more effectively than loose rubble piles that might absorb blast energy without producing coherent thrust. This method converts nuclear destruction into precise momentum transfer, using the violence of atomic explosions to gently nudge threatening asteroids away from collision courses with Earth. Nuclear weapons don't need to touch their targets to destroy them. Detonating nuclear devices in space near asteroids can provide more effective deflection than direct surface explosions. Standoff detonations work by bathing one side of the target asteroid in intense X-ray radiation from the nuclear fireball. This radiation penetrates several centimeters into the asteroid's surface, depositing enormous amounts of energy that instantly vaporizes subsurface material. The expanding vapor blows away from the heated surface, creating thrust that pushes the asteroid in the opposite direction. The optimal detonation distance balances radiation intensity against coverage area. Too close, and the explosion affects only a small portion of the asteroid's surface. Too far away, and the radiation becomes too diffuse to create effective vaporization. Typical standoff distances range from several hundred meters to a few kilometers, depending on weapon yield and asteroid size. Standoff explosions avoid many problems associated with surface detonations. They don't require precise impact timing or sophisticated penetration systems. The method works equally well against solid rocks, loose rubble piles, or icy objects. Multiple warheads can target different sides of an asteroid simultaneously for enhanced deflection efficiency. Space-based nuclear detonation transforms atomic weapons into precision deflection tools that can nudge asteroids without the mechanical complexities of direct impact systems. Nuclear weapons can either break asteroids into fragments or push them intact onto safer orbits. This fundamental choice determines whether we solve the asteroid problem or create hundreds of smaller disasters. Fragmenting large asteroids might seem appealing. Breaking one civilization killer into many smaller pieces reduces the energy of individual impacts. But fragmentation creates a new set of problems. The debris cloud spreads across a wide area, virtually guaranteeing that multiple fragments will hit Earth. Instead of one predictable impact site, we face dozens of unpredictable strike zones. Deflection preserves the asteroid's structural integrity while changing its orbital path. This approach requires precise energy application, enough force to alter the trajectory without exceeding the object's structural limits. Success depends on understanding the asteroid's composition, internal structure, and mechanical properties before detonation. Mission planning must account for the asteroid's discovery timeline. Objects detected decades before potential impact allow time for gentle deflection using smaller nuclear yields. Last-minute discoveries of large asteroids might require massive, explosive yields that risk fragmentation regardless of intent. The destruction versus deflection decision represents one of the most critical choices in planetary defense. Determining whether nuclear intervention eliminates the threat or multiplies it across multiple impact sites. Nuclear deflection effectiveness depends exponentially on how far in advance we act. Early intervention with small nuclear devices can prevent collisions that would require massive arsenals to stop at the last minute. The physics of orbital mechanics strongly favor early action. A tiny change in an asteroid's velocity, measured in centimeters per second, produces massive positional differences when accumulated over years. An asteroid deflected 20 years before potential impact needs only minimal velocity change to miss Earth by thousands of kilometers. Late intervention faces the mathematical reality of orbital mechanics. An asteroid discovered just months before impact would require velocity changes measured in meters per second to achieve the same missed distance. Such large deflections demand enormous nuclear yields that risk fragmenting the asteroid or require multiple simultaneous detonations. The timing advantage extends beyond simple physics. Early detection provides time for careful mission planning, multiple deflection attempts if the first fails, and verification that deflection efforts succeeded. Last-minute interventions offer no second chances and little opportunity to correct errors. Mathematical projections show that deflecting an asteroid 10 years before impact requires roughly 1% the nuclear yield needed for deflection just 1 year before collision. Early action transforms nuclear planetary defense from desperate last resort into manageable engineering challenge. Nuclear detonations in the vacuum of space produce no radioactive fallout that could contaminate Earth's environment. The absence of atmosphere fundamentally changes how nuclear weapons behave and eliminates most radiation hazards. Atmospheric nuclear explosions create fallout by lifting radioactive debris high into the atmosphere, where winds distribute contaminated particles across vast areas. Space-based detonations produce no such contamination because there's no air to carry radioactive material. The explosion products expand into vacuum and disperse harmlessly across cosmic distances. The primary radiation from space-based nuclear explosions consists of X-rays, gamma rays, and neutrons that travel at the speed of light. This initial radiation pulse lasts only microseconds and poses no long-term contamination risk. Any radioactive material created by the explosion remains localized near the detonation point and eventually disperses into interplanetary space. Earth's atmosphere and magnetic field provide additional protection against radiation from distant space-based explosions. The same atmospheric blanket that blocks cosmic radiation also shields the surface from nuclear explosions occurring beyond the atmosphere. Most of the radiation energy gets absorbed or deflected before reaching the ground. Space-based nuclear planetary defense eliminates the environmental concerns that make terrestrial nuclear weapons testing so problematic, allowing the full destructive power of atomic energy to be harnessed without contaminating the planet we're trying to protect. Using nuclear weapons in space requires navigating a complex web of international treaties designed to prevent the militarization of space. These legal frameworks could delay or prevent nuclear deflection missions during planetary emergencies. The Outer Space Treaty of 1967 prohibits placing nuclear weapons in orbit or on celestial bodies, though it allows unclear exceptions for peaceful purposes like planetary defense. The Comprehensive Test Ban Treaty forbids nuclear explosions in any environment, including space, though it provides potential exemptions for civilian applications. Multiple bilateral agreements between nuclear powers further restrict space-based nuclear activities. These treaties create legal uncertainty about when and how nuclear deflection missions could proceed. Emergency situations might require immediate action that bypasses normal diplomatic channels and international approval processes. But unilateral nuclear activities in space could trigger international incidents or arms control violations even when motivated by planetary protection. The legal complexity extends beyond treaty obligations to practical coordination challenges. Nuclear deflection missions require international cooperation for tracking, communication, and verification. Political tensions between nuclear powers could compromise mission effectiveness even when legal authorization exists. Resolution requires either pre-negotiated international agreements that authorize nuclear deflection under specific circumstances, or emergency protocols that allow rapid decision-making when humanity faces imminent extinction. The current legal framework assumes ample time for diplomatic consultation that planetary emergencies might not provide. Existing intercontinental ballistic missiles provide the foundation for nuclear asteroid deflection systems. These military delivery systems can be rapidly converted into planetary defense vehicles with minimal modification. ICBMs already possess the key capabilities needed for asteroid deflection missions. They can carry nuclear warheads beyond Earth's atmosphere, navigate through space using inertial guidance systems, and deliver their payloads with reasonable accuracy at interplanetary distances. The basic technology for reaching threatening asteroids exists in military arsenals worldwide. Conversion to planetary defense requires modifications to guidance systems, communication equipment, and mission profiles. Standard ICBM guidance works for ballistic trajectories within Earth's vicinity, but needs enhancement for interplanetary navigation. Deep space missions also require more sophisticated communication systems than military missiles typically carry. The delivery timeline favors military systems over purpose-built space vehicles. ICBMs can be prepared and launched within hours or days, while custom spacecraft require months or years of development and testing. When facing short-warning asteroid threats, existing missile systems provide the only realistic option for deploying nuclear deflection devices in time. Military delivery systems transform nuclear weapons from instruments of war into tools of species survival, repurposing humanity's most destructive technologies for the ultimate defensive mission. Nuclear deflection effectiveness varies dramatically depending on whether the target asteroid is solid rock, loose rubble, or something in between. Understanding internal structure determines whether nuclear intervention saves civilization or accidentally destroys it. Solid, rocky asteroids respond predictably to nuclear explosions. The coherent structure channels blast energy efficiently into momentum transfer, creating measurable velocity changes that produce reliable orbital deflection. Surface explosions vaporize material in predictable patterns, while standoff detonations heat the surface uniformly to create consistent thrust. Rubble pile asteroids, loose collections of debris held together by weak gravitational attraction, present completely different challenges. Nuclear explosions might scatter the rubble across space rather than deflecting it as a coherent unit. The fragments could create multiple smaller threats instead of eliminating the original danger. Predicting nuclear effects requires detailed knowledge of asteroid composition, density, porosity, and internal structure. Ground-based observations can provide limited information about surface properties, but internal characteristics often remain unknown until spacecraft arrive for close-up inspection. This uncertainty complicates mission planning and increases the risk of unexpected outcomes. The composition challenge forces nuclear deflection strategies to account for multiple scenarios. Mission planners must design nuclear interventions that work regardless of whether they encounter solid rock or loose debris, requiring flexible approaches that can adapt to whatever internal structure they actually find. The largest asteroids require more nuclear firepower than any single weapon can provide. Multiple warhead strategies distribute explosive force across space and time to maximize deflection effectiveness. Coordinated nuclear attacks can target different sides of a rotating asteroid, ensuring that explosive forces work together rather than canceling each other out. As the asteroid tumbles, successive detonations can apply thrust in the same direction relative to the object's center of mass. This technique multiplies deflection efficiency beyond what isolated explosions could achieve. Staged detonation sequences allow mission planners to observe the effects of initial explosions before triggering subsequent warheads. Early detonations provide real-time information about asteroid composition and structural response that helps optimize the timing and positioning of follow-up explosions. This adaptive approach maximizes the probability of successful deflection. Multiple warheads also provide essential redundancy for planetary defense missions. Nuclear weapons occasionally fail to detonate, guidance systems malfunction, or delivery vehicles suffer mechanical problems. Having backup warheads ensures that single-point failures don't doom the entire deflection mission when humanity's survival depends on success. The multiple warhead approach transforms nuclear deflection from a single desperate gamble into a systematic campaign that can adapt to unexpected challenges and overcome individual component failures. nuclear deflection becomes the only viable option when threatening asteroids are discovered too late for gentle intervention methods. This emergency scenario represents humanity's final chance to prevent cosmic catastrophe. Emergency nuclear missions operate under completely different constraints than planned deflection efforts. There's no time for detailed asteroid characterization, careful mission planning, or multiple deflection attempts. Decision makers must choose between the certain destruction of inaction and the uncertain risks of hasty nuclear intervention. The emergency timeline compresses years of normal planning into weeks or months. Existing nuclear weapons must be rapidly modified for space deployment. Launch vehicles must be commandeered from other missions. International cooperation must be achieved without extended diplomatic negotiations. Every aspect of the mission operates under extreme time pressure. Success probability decreases dramatically in emergency scenarios, but any chance of survival becomes worth pursuing when the alternative is certain extinction. Even poorly planned nuclear deflection offers better odds than simply waiting for impact. The mathematical reality of asteroid physics means that nuclear weapons remain effective even when deployed under suboptimal conditions. Emergency nuclear deflection represents humanity's insurance policy against cosmic surprises, a desperate but potentially effective last line of defense when all other options have been exhausted by insufficient warning time. Powerful laser systems can heat asteroid surfaces enough to create natural rocket engines. The concept sounds like science fiction, but the physics works through a simple process of controlled surface vaporization. When concentrated laser light strikes an asteroid's surface, it deposits enormous amounts of energy in a very small area. This intense heating instantly vaporizes rock and ice, creating expanding clouds of high-temperature gas that shoot away from the surface at several kilometers per second. The escaping vapor acts exactly like rocket exhaust, pushing the asteroid in the opposite direction through Newton's third law. The laser system can operate from ground-based facilities or space platforms positioned to maintain continuous illumination of the target asteroid. Multiple laser installations working together can focus their combined energy on the same surface region, multiplying the heating effect and increasing thrust production. A 10-megawatt laser array focused on a 500-meter asteroid could produce measurable deflection over months of continuous operation. The method works best on asteroids containing volatile materials like water ice that vaporize easily when heated. Rocky asteroids require higher power levels, but still respond to intense laser heating. Laser deflection transforms concentrated light into a contactless propulsion system that can nudge threatening asteroids without requiring spacecraft to make the dangerous journey to intercept them in deep space. Solar radiation exerts tiny but constant pressure on any surface it strikes. Attaching large reflective sails to asteroids can harness this solar wind to gradually push threatening objects onto safer orbits. Solar radiation pressure works because light particles, called photons, carry momentum despite having no mass. When photons strike a reflective surface and bounce back, they transfer their momentum to the surface through the collision. The force is incredibly weak, but it operates continuously as long as sunlight reaches the sail. A solar sail system requires deploying enormous reflective membranes, potentially several kilometers across, attached to or positioned near the target asteroid. These ultra-lightweight mirrors reflect sunlight in a controlled direction, creating steady thrust that accumulates over years. The sail orientation can be adjusted to optimize thrust direction as the asteroid moves through its orbit. The major challenge involves delivering and deploying such large structures in space. The sails must be lightweight enough for practical transportation, yet durable enough to survive years of exposure to space radiation, micrometeorite impacts, and thermal cycling between sunlight and shadow. Solar sail deflection transforms asteroids into spacecraft that use free solar energy for propulsion, providing unlimited operational time without fuel consumption or complex mechanical systems. Mass drivers launch chunks of asteroid material into space at high velocity, creating rocket thrust using the asteroid's own substance as fuel. This technique transforms threatening space rocks into self-deflecting vehicles. A mass driver operates like an electromagnetic railgun that accelerates small pieces of asteroid material to escape velocity using magnetic fields. The system extracts raw material from the asteroid surface, processes it into uniform projectiles, then launches these projectiles at several kilometers per second in a direction that produces optimal deflection thrust. The beauty of this approach lies in using the asteroid's own mass as propellant, unlike conventional rockets that must carry their fuel from Earth. Mass drivers have access to millions of tons of raw material already present at the target location. The system can operate for years while gradually reducing the asteroid's mass and changing its orbital velocity. Installing mass driver systems requires landing heavy equipment on the asteroid's surface and establishing power generation capabilities to operate the electromagnetic launchers. Solar panels or nuclear reactors provide the electricity needed to accelerate projectiles to high speeds. Automated mining systems extract and process raw material for continuous launch operations. Mass driver deflection turns asteroids into cosmic shotguns that fire themselves into safer orbits while slowly consuming their own mass in the process. The color of an asteroid's surface determines how much solar energy it absorbs versus reflects. Changing surface color through paint or powder coating can alter thermal properties enough to modify the asteroid's orbit over time. Dark surfaces absorb more sunlight and heat up to higher temperatures than bright surfaces that reflect most incoming solar energy. This temperature difference affects thermal radiation patterns that create tiny but persistent thrust forces. The effect, called the Yarkovsky force, can gradually push asteroids into different orbits over thousands of years, artificially modifying surface albedo, the scientific term for reflectivity, can enhance or reverse natural Yarkovsky effects. Coating one hemisphere of an asteroid with highly reflective material creates thermal imbalances that generate measurable thrust. The modification doesn't require massive equipment or dangerous operations near the asteroid. Deployment methods might include spacecraft that spray reflective particles onto asteroid surfaces or release clouds of reflective powder that settles onto the target. The coating material must adhere to the surface despite the asteroid's weak gravity and survive space radiation without degrading over decades of operation. Surface modification techniques transform the asteroid's interaction with sunlight from passive heating into active propulsion that can slowly but steadily alter orbital trajectories using free solar energy. Asteroids containing metallic materials can be deflected using powerful magnetic fields generated by orbiting spacecraft. This contactless method harnesses electromagnetic forces to alter asteroid trajectories without physical contact. Many asteroids contain significant amounts of iron and nickel from their formation in the early solar system. These metallic components respond to external magnetic fields through electromagnetic induction and direct magnetic attraction. A spacecraft equipped with superconducting magnets or high-current electromagnets can generate fields strong enough to influence metallic asteroid motion. The electromagnetic interaction works both ways. The magnetic field exerts force on the asteroid, while the asteroid's magnetic response creates equal and opposite forces on the spacecraft. Careful positioning allows the spacecraft to use this interaction to gradually tug the asteroid in desired directions while maintaining stable relative positions. The method requires detailed knowledge of asteroid composition to determine metallic content and magnetic susceptibility. Non-metallic asteroids composed primarily of rock and ice show little response to magnetic fields and cannot be deflected using electromagnetic techniques. Electromagnetic deflection represents the ultimate contactless manipulation technology, using invisible magnetic forces to guide metallic asteroids away from Earth collision courses without requiring physical interaction between deflection systems and their targets. Altering how fast an asteroid spins or which direction it tumbles can gradually change its orbital path through subtle thermal effects. This technique exploits the connection between rotation and natural orbital drift mechanisms. The Yarkovsky effect depends not only on surface temperature, but also on rotation rate and orientation. Asteroids that spin faster experience different thermal cycling patterns than slow rotators. The direction of rotation determines whether thermal thrust pushes the asteroid toward or away from the Sun, gradually modifying its orbital trajectory. Rotation modification can be achieved through several methods. Impacting one side of the asteroid with projectiles or focused energy beams can change its spin rate. Attaching gyroscopic devices to the surface can alter tumbling motion. Even landing spacecraft in specific locations can change mass distribution enough to affect rotation dynamics. The technique works best on smaller asteroids where rotation changes produce relatively larger effects on thermal balance. Large asteroids have too much rotational inertia to be easily modified, while very small ones may already rotate too fast for safe intervention without risking structural breakup. Rotation control transforms natural thermal effects from random orbital perturbations into controllable deflection mechanisms that can be fine-tuned to achieve specific trajectory modifications over extended time periods. Extracting valuable materials from asteroids reduces their mass while potentially generating thrust that alters orbital trajectories. Commercial mining operations could provide planetary defense benefits as profitable side effects. Large-scale mining involves removing thousands of tons of asteroid material to access valuable metals, water, and rare earth elements. This mass reduction directly affects the asteroid's gravitational interactions with planets and reduces the kinetic energy it would carry during any potential Earth impact. A smaller asteroid poses proportionally less threat even if its orbital path remains unchanged. Mining operations also create opportunities for controlled deflection through directed mass ejection. Instead of simply extracting material, mining systems can launch extracted resources in specific directions to generate net thrust on the remaining asteroid body. This technique combines resource recovery with orbital modification. The industrial infrastructure required for asteroid mining. Transportation systems, power generation, processing equipment can be adapted for deflection missions when threats are identified. Mining companies operating throughout the solar system would provide a distributed network of assets available for planetary defense when needed. Asteroid mining represents the only deflection technique that generates economic benefits while providing planetary protection. The combination of profit motive and species survival creates powerful incentives for developing the industrial capabilities needed for both commercial exploitation and emergency deflection operations. Deploying enormous inflatable mirrors around asteroids can create artificial solar pressure effects that gradually push threatening objects onto safer trajectories. These lightweight systems provide massive surface areas without requiring equally massive structural materials. Inflatable reflectors work by positioning large balloon-like structures near asteroids to redirect sunlight in specific directions. The reflected solar energy creates radiation pressure imbalances that generate net thrust on the asteroid. Unlike solar sails attached directly to the asteroid, inflatable reflectors operate from nearby space positions and can be much larger than structures that must be physically mounted. The balloons use ultra-thin metallized films that inflate to create parabolic or flat mirror surfaces several kilometers in diameter. These structures weigh only a few tons but provide reflective areas equivalent to small cities. Multiple reflectors can work together to focus reflected sunlight on specific asteroid regions for enhanced heating effects. Deployment challenges include accurately positioning the inflated structures relative to tumbling asteroids and maintaining proper orientation as both objects move through their orbits. Station-keeping propulsion systems must continuously adjust balloon positions to maintain optimal geometry despite gravitational perturbations and solar wind effects. Inflatable reflector systems transform lightweight balloon technology into cosmic-scale mirrors capable of redirecting solar energy to provide gentle but persistent deflection forces that accumulate over years of operation. Installing rocket engines directly on asteroid surfaces provides the most straightforward method of applying controlled thrust for orbital deflection. This approach treats asteroids like spacecraft that need propulsion systems rather than targets for external intervention. Surface-mounted thrusters use conventional rocket technology adapted for asteroid operations. The engines burn chemical propellants or use electric propulsion to generate thrust in precisely controlled directions. Multiple thrusters distributed across the asteroid surface can provide both translational and rotational control for complete trajectory management. The installation process requires landing spacecraft carrying thruster systems, drilling anchor points into the asteroid surface, and establishing fuel supply or power generation capabilities. Solar panels or nuclear reactors provide electricity for electric propulsion systems, while chemical thrusters require transported propellant supplies or fuel manufactured from asteroid materials. Thruster systems offer complete control over deflection timing, direction, and magnitude. Mission controllers can start and stop propulsion as needed, adjust thrust vectors in real time, and modify deflection strategies based on updated orbital calculations. This flexibility allows for precise trajectory corrections impossible with passive deflection methods. Surface-mounted propulsion transforms asteroids into controllable vehicles equipped with their own navigation and propulsion systems capable of executing complex maneuvers under remote control from Earth. The same gravitational slingshot techniques used to accelerate spacecraft can be engineered to deflect threatening asteroids using carefully planned encounters with major planets. This method harnesses planetary gravity as a cosmic steering mechanism. Gravitational assists work by having the asteroid pass close enough to a massive planet to experience significant gravitational deflection. The planet's gravity bends the asteroid's trajectory and can either speed it up or slow it down depending on the encounter geometry. These velocity changes translate into orbital modifications that can shift asteroid paths away from Earth collision courses. Engineering gravitational assists requires precise timing and trajectory planning. Small changes in the asteroid's approach velocity or direction can determine whether the planetary encounter produces helpful deflection or accidentally worsens the collision threat. Mission planners must calculate optimal asteroid trajectories years in advance and implement deflection maneuvers to ensure proper encounter conditions. The technique works best with Jupiter due to its enormous mass and gravitational influence. Even small trajectory adjustments that route an asteroid through Jupiter's vicinity can produce deflection effects equivalent to large-scale active intervention systems. Other giant planets provide additional opportunities for gravitational steering. Gravitational assist deflection transforms planetary gravity from a source of orbital complexity into a precision deflection tool that can redirect threatening asteroids using the solar system's own natural forces. Deploying hundreds or thousands of small robotic spacecraft working together can accomplish asteroid deflection tasks impossible for single large vehicles. Swarm systems provide redundancy, flexibility, and distributed capabilities that overcome many limitations of conventional spacecraft. Each robot in the swarm carries specialized equipment for specific deflection functions. Some might deploy solar reflectors, others could anchor thruster systems, while additional units provide communication relays and navigation beacons. The combined effect of many small actions can equal or exceed the capability of single large intervention systems. Swarm robotics offers tremendous resilience against equipment failures and operational hazards. Individual robot losses don't compromise the overall mission since redundant units can take over failed functions. The swarm can adapt to unexpected conditions by reallocating tasks among surviving units or changing operational strategies based on real-time performance feedback. Coordination challenges require sophisticated autonomous control systems that allow hundreds of robots to work together without constant supervision from Earth. Communication delays of hours between asteroid locations and ground control make real-time human coordination impossible. The swarm must operate as a self-organizing system capable of making collective decisions. Swarm deflection technology transforms asteroid intervention from single point of failure operations into distributed campaigns where the combined effect of many small robots can accomplish deflection objectives that exceed the capabilities of any individual spacecraft. Advanced holographic technology could create enormous virtual reflective surfaces using coordinated light interference patterns generated by multiple spacecraft. This cutting-edge approach might provide deflection capabilities without deploying physical structures in space. Holographic deflection works by positioning multiple spacecraft equipped with high-powered lasers in precise formations around target asteroids. The lasers generate coherent light beams that interfere with each other to create interference patterns. Regions where light waves either reinforce or cancel each other out. These patterns can simulate the optical properties of solid reflective surfaces. The virtual mirrors created through light interference can redirect solar energy just like physical reflectors, but without requiring massive deployable structures. The holographic approach allows real-time adjustment of mirror size, shape, and orientation by modifying laser output and spacecraft positioning. Multiple virtual reflectors can be created simultaneously using the same laser array. Technical challenges include maintaining precise spacecraft formations across distances measured in kilometers while coordinating laser systems to produce stable interference patterns. The slightest positioning error can destroy the holographic effect and eliminate deflection capability. Holographic deflection represents the most futuristic approach to asteroid intervention. using pure optical physics to create controllable cosmic mirrors from coordinated laser light rather than solid materials deployed in space. Protecting Earth from asteroid impacts requires coordination that transcends national boundaries. The United Nations Office for Outer Space Affairs and the European Space Agency now jointly operate the world's first international planetary defense system. This collaboration emerged from a simple reality: cosmic threats don't respect political borders. An asteroid discovered by American telescopes might threaten European cities while requiring deflection technology developed in Japan and launched from French Guiana. No single nation possesses all the capabilities needed for comprehensive planetary defense. The joint UN-ESA framework coordinates global asteroid tracking, threat assessment, and deflection mission planning. The system integrates data from over 30 countries while maintaining unified command structures for emergency response. When a genuine threat emerges, this international organization can authorize and coordinate deflection missions within weeks, rather than years. Legal authority comes from updated space law frameworks that grant the organization power to requisition national space assets during planetary emergencies. Member nations contribute funding, technology, and launch capabilities according to predetermined agreements that ensure rapid response regardless of political tensions. International planetary defense represents humanity's first truly global military alliance designed to fight threats from beyond Earth rather than conflicts between nations. Modern asteroid detection generates over 10 terabytes of observational data every night. Managing this information flood requires real-time global networks that can process observations from hundreds of telescopes simultaneously. The Planetary Defense Information Network operates like a cosmic internet that connects observatories worldwide through high-speed data links. When any telescope spots a potentially threatening object, the discovery gets automatically transmitted to processing centers on multiple continents within minutes. Computer algorithms immediately begin calculating orbital trajectories while human analysts verify the threat assessment. This global data fusion provides capabilities that no individual observatory could achieve alone. Multiple telescopes tracking the same object from different locations provide parallax measurements that dramatically improve distance and velocity calculations. Whether that blocks observations at one site doesn't interrupt global coverage, because other facilities continue monitoring from clear skies. The network also enables rapid follow-up observations of newly discovered threats. When one telescope identifies a suspicious object, the system automatically alerts other facilities positioned to continue tracking as Earth's rotation carries the original observer into daylight. This relay system ensures 24-hour coverage of emerging threats. Information sharing transforms isolated astronomical observations into coordinated global surveillance that can detect and track threatening asteroids with precision impossible for any single nation operating alone. Current space law was written before anyone imagined using nuclear weapons to save Earth from asteroids. Planetary defense requires completely new legal frameworks that authorize destructive technologies for protective purposes. The 1967 Outer Space Treaty prohibits placing nuclear weapons in space under any circumstances, but asteroid deflection missions might require nuclear devices specifically designed for peaceful planetary protection. Legal experts must distinguish between weapons of war and tools of survival while ensuring that defensive technologies don't become offensive capabilities. New treaties must address who has authority to launch nuclear deflection missions, under what circumstances such launches are permitted, and how to prevent abuse of planetary defense systems for military purposes. These agreements need approval from every nuclear-capable nation, plus major space-faring countries that could block or support deflection missions. The legal framework must also establish liability and compensation systems for deflection attempts that fail or cause unintended damage. If a deflection mission accidentally fragments an asteroid into multiple pieces that hit several countries, existing international law provides no guidance for determining responsibility or damages. International space law requires fundamental revision to authorize the extreme measures that planetary defense might demand while maintaining safeguards against the militarization of space. Building global planetary defense systems requires funding contributions from nations with vastly different economic capabilities and threat exposure levels. Fair cost distribution mechanisms ensure that every country contributes appropriately without placing impossible burdens on developing economies. The funding formula combines multiple factors including national GDP, space technology capabilities, population at risk, and geographic exposure to asteroid impacts. Wealthy nations with advanced space programs contribute larger shares, while developing countries provide smaller monetary contributions, supplemented by other resources like observatory sites or tracking stations. Current estimates suggest comprehensive planetary defense requires approximately $50 billion over 20 years for complete global coverage. This cost gets distributed among roughly 50 participating nations, with the largest economies shouldering the majority of expenses, while smaller countries contribute according to their means. The budget mechanism includes provisions for emergency funding when immediate threats require rapid deflection missions. Crisis scenarios trigger automatic financial commitments that bypass normal legislative approval processes, ensuring that bureaucratic delays don't prevent life-saving missions. Equitable cost-sharing transforms planetary defense from an impossible financial burden for individual nations into a manageable collective investment that provides comprehensive protection for all humanity. Effective planetary defense requires global technological capabilities rather than concentrating all expertise in a few advanced countries. Technology transfer programs spread critical knowledge and equipment to developing nations that provide essential geographic coverage for worldwide protection. The transfer initiative focuses on asteroid detection rather than deflection technologies to avoid proliferating dangerous capabilities while building essential observation networks. Participating countries receive telescope systems, data processing equipment, and training programs that enable them to contribute meaningful observations to global threat assessment. Regional centers in Africa, Southeast Asia, and South America now operate world-class asteroid detection facilities built through technology transfer partnerships. These installations provide coverage of sky regions that would otherwise remain unmonitored, eliminating dangerous blind spots in global surveillance networks. Training programs bring astronomers and engineers from developing countries to advanced facilities for months-long educational exchanges. These specialists return home with expertise needed to operate sophisticated detection systems and contribute high-quality observations to international databases. Technology sharing creates a truly global detection network where every participating nation contributes essential capabilities rather than simply receiving protection from more advanced space-faring countries. When astronomers confirm a threatening asteroid trajectory, the global early warning system must alert every nation within hours. Standardized communication protocols ensure that critical information reaches decision makers regardless of language barriers or political tensions. The warning system operates through multiple communication channels, including diplomatic networks, military command structures, scientific organizations, and public media outlets. Each channel carries identical threat information formatted for specific audiences. Technical data for space agencies. Simplified summaries for political leaders. Public safety instructions for emergency management organizations. Automated translation systems convert threat assessments into dozens of languages simultaneously while preserving technical accuracy. The messages include precise impact predictions, affected geographic regions, recommended evacuation procedures, and timelines for potential deflection missions. Warning protocols distinguish between different threat levels to prevent unnecessary panic while ensuring appropriate responses. Level 1 alerts indicate objects requiring additional observations. Level 2 warnings confirm probable impacts requiring emergency preparations. Level 3 alerts announce certain impacts and trigger full planetary emergency protocols. Global warning systems transform asteroid threat information from technical astronomical data into actionable intelligence that enables coordinated international response regardless of where the threat originates or which populations face danger. Private space companies now provide launch capabilities, technological innovation, and operational flexibility that government space agencies cannot match. Commercial participation has become essential for rapid response planetary defense missions. Companies like SpaceX can prepare and launch deflection missions in weeks rather than the years required by traditional government space programs. Private facilities operate with streamlined decision-making processes that eliminate bureaucratic delays common in international government cooperation. When time becomes critical, commercial companies provide the only realistic option for rapid deployment. Private space companies also drive technological innovation through competitive development processes. Commercial competition has reduced launch costs by over 90% while improving reliability and operational flexibility. These advances make planetary defense missions economically feasible where traditional government programs would be prohibitively expensive. The commercial sector provides redundant launch capabilities that ensure deflection missions can proceed even when government facilities suffer technical problems or political complications. Multiple private companies operating from different countries create backup options that prevent single points of failure from compromising planetary protection. Private space industry participation transforms planetary defense from government monopoly into competitive commercial service that provides better capabilities at lower costs with greater reliability than traditional space programs. Future planetary defense systems will operate autonomously using artificial intelligence and robotic technology to detect threats, plan missions, and execute deflection operations without requiring human intervention for routine decisions. AI systems can process observational data from thousands of telescopes simultaneously while identifying threatening asteroids within minutes of discovery. Machine learning algorithms continuously improve their threat assessment capabilities by analyzing patterns in asteroid behavior that human observers might miss. These systems never sleep, never get distracted, and never make calculation errors due to fatigue. Autonomous deflection systems could launch and operate spacecraft without waiting for human approval during emergency situations. AI mission planners can design optimal deflection trajectories, select appropriate technologies, and coordinate multiple spacecraft operations with precision that exceeds human capabilities. Robot systems can adapt to unexpected problems during missions while maintaining focus on planetary protection objectives. The ultimate goal involves creating fully automated planetary defense networks that can detect, assess, and deflect asteroid threats from discovery through successful mission completion. Human oversight remains important for major policy decisions, but routine operations would proceed under AI control. Artificial intelligence transforms planetary defense from human-dependent crisis management into autonomous protection systems that provide continuous safeguarding regardless of human availability or decision-making capabilities. Protecting Earth from surprise asteroid impacts requires maintaining deflection systems in constant readiness rather than building them only after threats are discovered. Permanent standby operations ensure immediate response capability when time becomes critical. The standby system maintains fully fueled spacecraft equipped for deflection missions at launch facilities worldwide. These vehicles can deploy within 72 hours of threat confirmation, rather than requiring months of preparation and assembly. Pre-positioned equipment eliminates the time delays that could prove fatal when dealing with short-warning asteroid discoveries. Continuous readiness extends beyond launch vehicles to include trained personnel, communication networks, and decision-making procedures that can activate instantly. Mission planning teams maintain updated deflection strategies for various threat scenarios while staying current on technological capabilities and operational procedures. The permanent standby approach requires significant ongoing investment to maintain equipment, train personnel, and update technologies even when no immediate threats exist. But this insurance premium provides the only realistic protection against asteroid discoveries that allow insufficient time for building deflection systems from scratch. Standby planetary defense creates a cosmic fire department equipped to respond immediately to existential emergencies rather than trying to build fire trucks after the alarm sounds. Asteroid impacts represent the most preventable existential threat facing human civilization. Unlike climate change, pandemics, or nuclear war, asteroid threats can be completely eliminated through adequate technological preparation and international coordination. Risk management experts classify asteroid impacts as high-consequence, low-probability events that justify significant preventive investment despite their rarity. The potential consequences, ranging from regional devastation to species extinction, far exceed the costs of comprehensive planetary defense systems. Insurance mathematics clearly favor building protection rather than accepting risk. Modern civilization faces multiple existential threats that require different approaches and timelines. Asteroid defense provides the clearest success story where technology can completely solve a major threat category. Success in planetary defense demonstrates humanity's ability to cooperate globally for species survival while providing tested systems for addressing other existential risks. The Planetary Defense Framework creates institutional mechanisms for international crisis response that extend beyond asteroid threats. The same organizational structures, legal authorities, and funding mechanisms developed for cosmic protection can adapt to address other global emergencies requiring rapid technological solutions. Asteroid defense establishes the precedent that human civilization can identify, plan for, and prevent its own extinction through coordinated application of science technology. An international cooperation rather than simply hoping that natural disasters won't occur during our lifetimes.